Welcome back to Educator.com. Welcome back to Linear Algebra. Today we're going to talk about the matrix of a linear map. Okay, let's just jump right in. We've already seen that when you have a linear map from Rn to Rm, let's say R3 to R5, that linear map is always representable by some matrix, a 5 by 3 map in this case, always. So today we want to generalize that result and deal with linear maps in general, not necessarily from one Euclidean space to another Euclidean space, but any vector space at all. So let's go ahead and start with a theorem. Some people might call this, most of you are familiar, of course, with the fundamental theorem of calculus. There's also something called the fundamental theorem of algebra that concerns the roots of a polynomial equation. In some sense, if you want, this theorem that I'm about to write, you can consider it the fundamental theorem of linear algebra. It sort of ties everything together, if you want to call it that. Some people do, some people don't. It certainly isn't historically referred to that way, the way the others are, but this sort of brings the entire course that we've done. Everything has sort of come to this one point. So let's go ahead and write it down very carefully and talk about it, do some examples. Theorem. Okay. The statement of this theorem is a bit long, but there's nothing strange about it. Let L from V to W be a linear map from an n-dimensional vector space into an m-dimensional vector space. And again, we're talking about finite dimensional vector spaces always. We're not talking about infinite dimensional vector spaces. There is a branch of mathematics that deals with that called functional analysis, but we're concerned with finite dimensional vector spaces. N-dimensional vector space, sorry about that. Okay, we will let S, which equals the set V1, V2, so on to Vn, be a basis for V. And T, which equals W1, W2, so on and so forth, onto Wm, be a basis for W, the arrival space. I really love referring to them as departure and arrival space. It's a lot more clear that way. Then the M by N matrix A, whose jth column is the vector L of V sub j, the coordinate vector with respect to t, and I'll explain what all of this means in just a minute, don't worry about the notation, is the matrix associated with the linear map. And has the following property. L of x with respect to t is equal to a times x with respect to s. Okay, so let me read through this and talk a little bit about what it means. So L is a linear map from a finite dimensional vector space, to another finite dimensional vector space. The dimensions don't necessarily have to be the same. It's a linear map. Okay. S is a basis for V, the departure space. T is a basis for the arrival space. Okay. Then there's a matrix associated with this linear map of two arbitrary vector spaces. There's a matrix associated with this. And the columns of the matrix happen to be, so for example, if I want the first column of this particular matrix, I actually perform L, the linear map, I perform it on the basis vectors for the departure space. And then once I find those values, I find their coordinate vectors with respect to the basis t. You remember coordinates? And once I put them in the columns, that's the matrix that's associated with this linear map. The same way that a matrix was associated with a linear map from one Euclidean space to another, R4 to R7, giving you a 7 by 4 matrix. Well, remember we talked about coordinates. A vector can be represented by a linear combination of the elements of the basis. So if we have a basis for the particular space, all we have to do is the coordinates are just the particular constants that make up that linear combination. So in some sense, we're sort of associating a 5-dimensional random vector space with R5. We're giving it numbers. That's what we're labeling it. That's what we're doing. And it has an interesting property that if I take some random vector in the departure space and I perform some operation on it, and then I find its coordinate vector with respect to the basis t, it's the same as if I take that x before I do anything to it, find its coordinate vector with respect to s in the departure space, and then multiply it by this particular matrix. I get the same answer. So let's just do some examples, and I think it'll make a lot more sense. So